Next, let's look at some circuits that we can use to control motors. Now, motors have a couple of issues that we need to deal with when we're designing circuits to control them. The first is that motors require a lot of current. So in a microcontroller or a logic level device, the most we can expect any particular pin is in the milliamp, tens of milliamps range, and often motors require a lot more current to run, anywhere from a couple hundred milliamps up to many hundreds of amps if we're dealing with large industrial equipment. So we have to figure out a way to scale the small current signals that come from our microcontrollers up to the size of whatever the motor is. And we have to do that safely so that we're not putting any load on our microcontroller. Motors often require different supply voltages than the logic that we're dealing with. 5 volts or 3.3 volts on our board is often not enough pressure, so to speak, to make the motor coils move. So we often have to use more, typically 9 to 12 volts. And motors are electrically noisy. We have spinning magnets, we have contacts on brushless motors that are creating tons of noise. When the motor stops, it generates a lot of noise, and we have to figure out how we can isolate the electrically noisy environment of our motors from the power supply that is also driving our digital electronics, which require very clean, very noise-free environment. So this is part of the analog digital divide, and we're going to look at some ways to handle this. You might think, oh sure, I can just when I turn a pin on my microcontroller, I can just hook that directly up to a motor and it should spin, right? No, that is a terrible idea. What happens is, as the motor starts to spin up, it is going to draw more and more current, and it's going to try and pull that current through the pin, and there's no limiting there. It'll just burn out the pin, and it could damage the microcontroller itself, and you'll end up with a dead microcontroller, a very expensive part to replace. So we definitely want to avoid that. Right? So the way that we approach this is to use a transistor. And the idea here is we want to use a transistor as a basic kind of switch. We want to have this be electrically controlled by our digital logic. We give it 5 volts. We can switch 12 volts onto the motor without worrying about it. This resistor here helps limit the amount of current that goes into the transistor from the microcontroller. 1 kilo ohm is plenty, typically. And in this case, we're doing a active low behavior, right? So when we drive this to 0, that drops down the base, which allows current to flow into the motor. And the reason why we're doing active low is because if we were doing active high and put it on the other end, we would need to overcome the supply voltage to get the transistor to open. So in this case, we want the we can turn off the transistor with any voltage we want by adding 5 volts to it, but to activate it, we can drive it active low, and that causes current to flow through it. So this is a great simple on-off motor control. When we only need unidirectional behavior, when we only want to turn the motor on in one direction, the same direction every time, that's a technique that we can use. If we want to do bidirectional motor control, it gets way more complicated. We have to use what's called an HBridge circuit. And this is an HBridge circuit because it makes an H of 4 transistors, make the 2 sides of the H, and the motor makes the bridge between them. And the idea here is we use 2 input bits. So we can turn on the motor, we can turn off the motor, and we can also control the direction of the motor. So if I have a 0 on input A and a 1 on input B, current flows through the VCC, through the motor in this direction, and the motor rotates in one direction. If we flip those and go the opposite direction, if I have a 0 on input B and a 1 on input A, then current flows from VCC on this side through the motor in the opposite direction and goes down to ground. So we have that option. If they're both 0, that's a braking condition. If they're both 1, and because these are active high, or active low, then if they're both 0, then that's just an off idle position for the motor. Building these 8 types of H-bridges by hand is kind of annoying. I've done it, I've tried it a couple of times, and getting the transistors in the right configuration and making sure you use NPN in the top and PNP in the bottom, and making sure everything is configured properly and all that kind of stuff is a total pain. So thankfully there's a couple of nice chips for small scale electronics. I have liked the L293D that's made by, and both of these are actually made by Texas Instruments, and the SN754410. Both of these are quadruple half H-bridge chips, and basically each one is half of one of these H-bridges. And it's got 4 of them, so that means I can control 2 whole motors up to an amp with the SN754410, up to half an amp with the 293D. So for small motors, you can use those and configure them pretty simply to do whatever you need. Now, the problem is with most motors, with the particularly DC motors, is we have a bunch of noise that occurs when we stop the motor. And the idea here is we have a magnet that's energized. That's the rotor of the motor. And as it's spinning, as we're applying power to it, it has generated a magnetic field and it's spinning. When we turn power off, as we can see here in this diagram, we're applying 5 volts to the motor, and it keeps spinning, and we have our winding signal. So we have the amount of energy that's going through this thing, right? Yeah, the amount of energy that's going through the motor. When it stops, that motor changes from being a motor to being a generator, because the inertia of the rotor spinning actually carries through, and that causes a giant opposite energy spike. Also, the magnetic fields are collapsing at the same time, which also resists the flow of current. So we have what's called a back EMF, a back electromagnetic field that basically pushes back on the system and causes a big negative spike. And the way that we get around that is by adding what's called EMF diodes that go from the ground to 12 volts. And what this does is when the motor is going into that generating mode, when the field is collapsing, the positive current starts going back the opposite direction, and we want it to have a nice clean path to go back to 12 volts. We basically want to short circuit it so that it allows it to flow and push back, and that dissipates the energy as it goes through, as the motor stops and slows down and stops. For bidirectional motor control, we have to use 4 diodes in a similar configuration, always going towards VCC. And what this does is it provides the same thing, but for both directions. No matter what direction the motor is spinning, it's going to allow current to flow back into the power supply safely without causing any spikes on ground, which can interrupt our digital electronics and stuff like that. We also have the problem that in brushed DC motors, as the commutator spins, we're breaking and making new electrical connections. And that can often cause little sparks to occur, and those little sparks are radio emissions. Those are like little lightning strikes. And if you ever heard the radio in a thunderstorm or something like that, you can hear lightning strikes because they are broadband electrical interference. Now, to cancel these out, and this happens, the commutator noise is what they call it. The commutator noise happens every single time the motor goes around. So as you'll see little spikes, as you can see on this diagram, that are caused by the motor windings making contact in a new direction every single time. So the way we mitigate that is by putting a small ceramic capacitor across the terminals of the motor. And what this does is it smooths out those little spikes and damps down the electrical noise. It damps down the radio noise that's being generated. You'll still get some from the commutator itself, but it isn't being amplified by the rest of the circuit. So it gets snubbed right there. And we use a very small capacitor because this is typically extremely high frequency noise, and we want to damp it down as much as possible. In a bidirectional motor control, it's the same configuration. We put our snubbing capacitor as close to the motor terminals as possible. Often in small devices, you'll see it actually soldered directly to the motor on the body of the motor, and that's a great way to filter out this electrical noise. Now, we've been looking at primarily control circuits for DC brushed motors, but for DC brushless motors, it's very similar, except we're controlling individual coils, and those coils are need to be coordinated and driven bidirectionally or monodirectionally in the same way. So we would use arrays of these things. For example, one of our HBridge chips, the quadruple HBridge chips, could drive 2 coils in 2 directions. So that would be 2 motors, basically, because you can think of a general motor, one single brushed motor, as 1 coil that I can drive in 2 directions. In a stepper motor or something like, or a brushed DC motor, or a brushless DC motor, they have multiple. They could have 2 coils, 4 coils, sometimes 3 coils, all kinds of weird configurations. And depending on how they're configured, we can use circuits just like this and control them in different patterns to make the motors move back and forth and go in different directions.